All right, let's dive in. Picture this. You've got millions of items to sort, and you absolutely cannot afford any surprises. You need performance that's totally rock solid, predictable every single time. Well, that is the exact promise of Merge Sort, and today we're going to break down how it delivers on that guarantee.
So yeah, that's the big question, right? When you can't have performance spikes, when consistency is absolutely everything, how do you build a sorting algorithm that you can trust 100%? This isn't just some academic puzzle, it's a critical question for database systems, large-scale data processing, you name it.
And that brings us right to Merge Sort's main selling point. It's all about that promise of predictable performance. It's a guarantee that you'll see other very famous algorithms can't always make. The secret sauce behind Merge Sort is this really powerful strategy called divide and conquer. And the idea is, well, it's kind of brilliant and super simple. Don't try to tackle a huge, messy problem all at once. Instead, just break it down into smaller, identical problems and keep breaking them down until they become so simple they're trivial to solve. Then you just stitch those simple solutions back together. So what does it actually look like? It's really just a clean three-step dance. First, you divide. You just split the list all the way down. Second, you conquer. And here's the cool part. A list with just one item in it is already sorted, right? So this step is pretty much free. And third, the most important part, you combine by merging these tiny sorted lists back together until you only got one fully sorted list left.
Okay, let's actually see this in action, starting with that divide phase. This is where we just methodically chop our big problem into tiny, manageable pieces.
So here's our test subject, a simple, totally jumbled array of 6 numbers. Our mission, should we choose to accept it, is to get this thing into ascending order, using our new strategy. First move, super simple. We just chop it right down the middle. Now, instead of one problem, we have 2 smaller, totally independent problems to solve, the left half and the right half.
And we just keep doing that. We keep splitting recursively over and over again until we physically can't split anymore. So what are we left with? A bunch of tiny lists, each with only one number. And hey, guess what? A list with one number is already sorted by definition. Boom. Division is done.
Okay, so we've broken everything down into dust. Now for the really elegant part, the magic trick, the merge step. This is where we actually create order out of all that chaos. Seriously, this is the best way to think about it. Imagine you have 2 lines of people, and each line is already sorted by name. To create one big sorted line, you just look at the person at the front of each line, pick whoever comes first alphabetically, and send them to the new line. You just keep doing that until one line is empty, then everyone from the other line just joins the end. Simple. Okay, let's actually walk through it. Imagine we've already done one level of merging. Now we have 2 sorted little arrays. 3, 8, and 1, 5. So we look at the first number in each list. We've got a 3 and a 1. Which one's smaller? The 1, obviously. So that's the first number in our new merged list. And we just keep rinsing and repeating that. Next up, we're comparing the 3 and the 5. 3 is smaller, so it goes next. Now we're looking at the 8 and the 5. 5 wins. And what's left? Just the 8. So we pop that on the end. The result is a new, bigger sorted array, 1, 3, 5, 8. We've conquered that level. All right, we are at the final boss level for our little example here. We've got our fully merged left half and the sorted right half, which is 4, 9. Now we're just going to do that exact same merge dance one last time. And voila! Just like that. By systematically comparing and merging, we get our final, completely sorted array. It's a bunch of simple steps that lead to really powerful, predictable behavior. Okay, so we get how it works. It's clever, but isn't any good? What's the actual cost for all this guaranteed predictability? This right here, this is the golden ticket for merge sort, theta of n log n. Now, that theta symbol is important. It means this is what you get, period. It's not a maybe or a best case thing. The time it takes to run grows predictably with the size of your list, whether that list is already perfectly sorted or a complete and total mess. And this table just makes it crystal clear. I mean, look at the time complexity. Best, average, and worst case are all identical. That is the predictability we've been talking about. But, and this is a big but, check out that last row. Space complexity, O of n. That's the catch. That's the price you pay. To do that clean merge step, merge sort needs extra memory, about the same size as the original array. So let's break down what these properties actually mean for you. Stable? That's a huge win. It means if you have two identical items, they stay in their original order, which is super important for complex sorting. But it's not in place because of that extra memory it needs. And adaptive? Nope. It doesn't care if the data is almost sorted already, it's going to do the same amount of work every single time.
Right, so no algorithm is an island. Let's put merge sort in the ring with some other sorting heavyweights and see how it holds up.
This chart tells the whole story, really. Look at Quicksort. Yeah, it's usually faster and way better on memory, but it has that terrifying O of n squared worst case just lurking in the shadows. HeapSort? It matches the time guarantee and uses almost no extra space, which is awesome, but it's not stable. And that's where you see merge sort's sweet spot. It's the stable, guaranteed performer if you can afford the space. So let's get down to brass tacks. When do you actually pull merge sort out of your toolbox? First, when failure is not an option, you need that guaranteed performance no matter what. Second, when stability is a must-have. Third, and this is a big one, it's fantastic for external sorting, like sorting a file that's way too big to even fit in your computer's memory. And of course, you use it when you've got enough memory to spare. Look, if you're going to walk away with just one sentence, make it this one. Merge sort is stable, it's predictably n log n, and it's memory hungry. Those three things define what it is and where it shines.
And that really brings us to the big question you have to ask yourself as an engineer. For what you're building with your specific needs, is that ironclad guarantee of perfect predictability worth the price of extra memory? And the answer, like with so many things in engineering, it depends.